Okay, hello everyone. I'm Pavel Mačák, and today I will be talking about shape optimization using so-called adjoint method with the application on compressor blade cascades. We can define the optimization problem as follows. We have some primal variables phi, which in our case will be the kinematic pressure and velocity. Design parameters g, which for shape optimization will be connected to the shape of the domain, to the shape of the airfoil, for example. A cost function j, which for each combination of primal variables and design parameters is able to tell us how good or bad our current design is. And lastly, constraint equations, which in our case will be the Navier-Stokes equations for fluid motion. Then we can say that the optimization problem is to find a combination of design parameters and primal variables, which minimizes the cost function while keeping the constraint equations valid. All right, so the adjoint optimization method belongs to the family of gradient optimization methods. These methods update the design parameters based on the gradient of the cost function with respect to the design parameters. Typically, this is the most challenging task and time-demanding task to get this gradient. In comparison to, for example, finite differences, which are usually used to approximate this gradient, the adjoint method has a big advantage in the sense that the computational time to approximate this gradient is independent of the number of design parameters. This is very favorable for our problem of shape optimization. However, it requires simulating or solving a new set of partial differential equations, and we will see why now. So this comes from the method of Lagrange multipliers, which is used to solve a constraint extrema problem, which our optimization problem inherently is. It defines a new cost function using so-called Lagrange multipliers xi, and says that the solution to our original problem is such a combination of primal variables, design parameters, and the Lagrange multipliers for which the total variation of the new cost function is equal to 0. Since the variations of each variable are arbitrary, we need each of these three terms to be equal to 0 independently. So from the first term, we will derive the new system of partial differential equations. From the second term, we will approximate or get this gradient in the end. And the last term is just r equal to 0, which are our original governing equations, the Navier-Stokes equations for fluid with constant density in stationary state. These governing equations are written here. They are very well known, and from these we derive the adjoint equations. Maybe just a side note here, the Lagrange multipliers are called adjoint variables in this adjoint method. So we will have an adjoint velocity and adjoint pressure. And after deriving these equations, after getting these adjoint equations, they look like this, these two last lines here. They are fairly similar to our governing equations, with a few important differences though. Firstly, they are linear in the adjoint variables. They are linear in v and q. Secondly, there is an opposite sign at the convective term here, which tells us that the information in the flow field is convected upstream instead of downstream, like it is in the original equations. And lastly, we have some new source terms on the right here, which depend on the definition of our original cost function. All right, enough of mathematics. And now let's get to the application. So we will be trying to optimize the shape of an airfoil inside a blade cascade. The typical computational domain looks like this on the right here. So we have an inlet boundary, an outlet boundary, the airfoil in the middle, and periodical boundary condition on the top and bottom, which should represent the blade cascade itself. We will be trying to change the outlet stream angle alpha 2 as defined here at the outlet boundary, which is an important parameter when designing turbomachinery, because the following component, for example, after the compressor, usually has a set desired inlet angle of stream, and therefore we need to sometimes change it in the component before. So this is what we will be trying to do. Now we can define the cost functions themselves. So the angle of stream at the outlet can be computed from this relation, so from the components of the velocity at the outlet. And this leads to a so-called direct formulation. So for a given alpha2, the outlet stream angle, we can compute some target value of y component of velocity and define the cost function as a quadratic difference from this target value. So this will be an integral over the outlet boundary here. Another approach which I used is a so-called indirect formulation, which uses, instead of the velocity, it uses the force by which the airfoil itself interacts with the stream and therefore bends the flow, so to say. This formulation is defined by an integral over the airfoil itself. So the integral is a boundary integral, but over a different boundary. And another difference, very important one, is that this indirect formulation uses all the available information from the flow field. So it uses all the variables, the kinematic pressure, velocity, and also the turbulent variables as well. So, and the target values for the optimization here on the right are not so important. What is important here to note is that we will be trying to change the original outlet stream angle from -4 degrees up to 8 degrees with respect to the original design angle, which was the 21.46 degrees. All right, so far we only talked about the design parameters in general. Now we need to specify them a bit more. The design parameters need to be connected to the shape of the airfoil itself, and the approach that was chosen here are so-called volumetric B-splines. You can see the control points of these B-splines in the picture on the right. And there's also denoted that some of these control points have restricted movement. This is done in order to keep the mesh valid, not to move, for example, the periodical boundary, and also so that the airfoil itself doesn't stretch or shrink in the chord line direction. All right, so finally some results. Here on this slide, you can see two plots of a so-called residual. It is basically just a relative difference between some target value of alpha2 and the alpha2 in some iteration I. So on the left, we have the direct formulation, on the right, the indirect formulation. What is very interesting result here is that the optimization algorithm needs exactly the same amount of iterations to converge to get under this pink line, which is 1% relative difference. It needs the same amount of iterations to converge for both direct and indirect formulation. However, what we can see here, that the indirect formulation has somewhat a smoother run of the residual itself. This is probably because of the thing I mentioned, that the indirect formulation uses much more information from the flow field to approximate the gradient, and therefore it can be assumed that it is a bit more precise, and therefore we don't have such big jumps in the residual as for the direct formulation. Another very intriguing result is the optimized shape itself. Here it is for the target angle of -4 degrees and the 12th iteration for both indirect and direct formulation. In the picture on the right, the black line is the original shape, and the red and blue lines are the optimized shapes for direct and indirect formulation. What we can see from this, or maybe cannot see from this, is that we get identical shapes for both formulations, which basically tells us that with respect to quality of the results, it doesn't matter which of the cost functions we used, which of the formulations we used. Finally, what I did was a validation of these results using a more suitable turbulence model for internal aerodynamics. Originally, I used the Spallard-Almaraz. Now, the better one, which is commonly used in internal simulations of internal turbomachinery, is the K-omega SST turbulence model. Again, we have the residual graph here on the left, and here we can see that for target angle changes of +8 and -4 degrees, we no longer get under the pink line of convergence. So in the sense of this validation, the methodology only worked for changes of the angle from -2 up to +6 degrees. This can be partially explained by the figure on the right, where we have a relative difference in velocity magnitude between the two simulations, between the simulation with Spallard-Almaraz and K omega SST. As we can see, here at the trailing edge at the suction side of the airfoil, the Spallard-Almaraz model predicts a much higher velocity magnitude, and therefore we can say it probably predicts the separation of the flow here wrongly. And this has obviously a huge impact on the outlet angle of stream. All right, just to sum up, what was done is this work. New cost functions for the adjoint optimization methods were implemented using the open foam framework, and they were used to optimize an airfoil in a blades cascade. Both cost functions were compared, and the results were validated using a more suitable turbulence model for internal aerodynamics simulations. All right, that was all from me. Thank you for your attention, and if you have any questions, please go ahead.